Hello, my dear students. Today, in this lecture, let us solve some of the numericals on steam nozzles. In my previous lecture, I've explained how to use the Molière diagram for solving the problems on steam nozzles. Here, in this lecture, let us solve problems both using steam tables as well as Molière chart. Let us go to the first problem where in the first problem it says the steam expands from 3 bar to 1 bar in a nozzle. So that means steam entering the nozzle is at 3 bar and exits at 1 bar. The initial velocity of the steam is given as 90 meters per second and the temperature of the steam entering as 150 degrees centigrade. Determine the exit velocity of the steam. So here you have two cases. If the expansion of the steam is isentropic and if the expansion of the steam is with nozzle efficiency of 95%. This problem was asked in July 2019. Okay. See now, let us see this HS diagram where it says the pressure entering the nozzle is 3 bar and 150 degrees centigrade. That means, so go to this 3 bar pressure where it cuts the temperature of 150 degree. So mark the point as 1. Okay, that is using the Molière chart. But here in this problem, since it is very simple, let us solve using steam tables. So go to the steam tables, superheated tables, and for 3 bar 150 degree centigrade, get the value of H1 and S1. Then, first case he has said expansion is isentropic in the nozzle, and then you need to find the exit velocity of the steam. So isentropic expansion, that means 1 to 2, it is vertical line. So S1 will be equal to S2. This similar problem we have already solved in vapor power cycles. So S1 is obtained directly from the superheated table and S2, since it is in the wet region, you need to find the value of X2. So S1 is equal to SF2 plus X2 into SFG2. So from the steam tables, for 1 bar pressure, get the value of SF2 and SFG2. So it is shown here. So SF value, SFG value, HF value, HFG value. All these values are obtained from the pressure, from the steam tables for pressure 1 bar. So S1 is nothing but the superheated, S1 is in superheated region, so it is 7.0771. That will be equal to SF, that is 1.3027 plus X2 into SFG2, 6.057. Get the value of X2. That means X2 is the dryness fraction of the steam at the exit of the nozzle. Once you get the X2, you have to find the value of H2. So H2 is equal to HF2 plus X2 into HFG2. So if you substitute, you'll get the value of H2. Since the expansion is isentropic in nature, the velocity at the exit of the nozzle is given by V2 is equal to square root of V1 square plus 2 into H1 minus H2. This equation derivation is shown in one of my previous lecture. So this velocity will be equal to, what is the initial velocity is given 90. So 90 square plus 2 times H1 and H2. These two values which are obtained above. Please don't forget to multiply by 10 power of 3 because all the H values you find out will be in kilojoules per kg. But here you need to substitute in joules per kg. Hence, please make sure you use this 10 power 3 without fail. So you get the velocity of 624.7 meters per second as the exit velocity. Next is the first case. In the second case, they say there is a Nozzle efficiency of 95%. That means due to friction, the nozzle is not 100% efficient, and the steam which is coming out will, and the enthalpy of the steam which is coming out will be higher than the ideal case. So ideal case it was H2 here, but here it is H2 dash, which is higher than the ideal case. So how to find that H2? So H1, what is the nozzle efficiency given as actual enthalpy drop divided by isentropic enthalpy drop. Actual enthalpy drop here is H1 minus H2 dash. So nozzle efficiency equals H1 minus H2 dash divided by isentropic drop H1 minus H2. Okay, so H1 minus H2 dash will be equal to what? Nozzle efficiency into isentropic enthalpy drop. We know the value of H1 and H2. We do not know the value of H2 dash. Hence, we use the formula H1 minus H2 dash as nozzle efficiency into H1 minus H2 in the velocity equation. So V2 dash will be equal to V1 square plus 2 times H1 actual enthalpy drop. So H1 minus H2 dash. So what is H1 minus H2 dash? It will be equal to nozzle efficiency into H1 minus H2. So that we are substituting here the value here. And we get the value of velocity as 609.29 meters per second. So due to friction, the isentropic or the theoretical velocity should have been 624.7, but due to friction, there will be some loss in the energy, hence the velocity reduces to 609.29 meters per second will be the exit velocity. Okay. Now, let's go to the next problem. The second problem says the steam is allowed to expand in a set of nozzles from 10 bar to 100 degrees centigrade. Whenever they give a temperature, make sure normally it will be superheated steam. So 10 bar 200 degrees centigrade is the condition of the steam which is entering the nozzle, and it is expanded to pressure of 5 bar. What type of nozzle is it? We need to find the type of the nozzle. Normally type of the nozzle means there will be two types which will be we use here. One is the convergent nozzle, other one is the convergent divergent nozzle. So next, let us see how to find out the type of the nozzle. Next, neglecting the initial velocity of the stream. That means V1 velocity, let us put it as 0. We'll neglect it. Calculate the minimum area of the nozzle required to allow the flow of 3 kg per second under the given conditions. So we need to find out the nozzle minimum area of the nozzle. So assume the expansion of the steam to be isentropic. So that means there is no frictional losses. That means all frictional losses are neglected here. Now, so what is the condition? P1 is equal to 10 bar 200 degrees centigrade and exit pressure is 5 bar and the mass flow rate is 3 kgs per second. These are the given data. So, since we do not know whether it is a convergent nozzle or convergent divergent nozzle, first thing we need to find out is you use the critical pressure ratio formula and get the P2 pressure. So P2 will be P2 by P1 is equal to 2 by n plus 1 whole power n by n minus 1. This is the formula, critical pressure ratio formula, which is again derived in the previous lecture. So P2 will be equal to P1 into 2 by n plus 1 whole power n by n minus 1. We know the value of P1, that is entry pressure, and n, since the steam is entering with superheated, so the n value you have to assume as 1.3, and this normally n value varies from 1.135 to 1.3. If the steam at the entry is dry saturated, you have to use the value of n as 1.13, but here it is superheated, so we use the value of n as 1.3. Then find the pressure P2. P2 is getting as 5.46. But The exit pressure, they say it is 5 bar. That means further expansion of the steam has to occur to reach the pressure of 5 bar. That means the nozzle which we use is a clearly says that it is a convergent divergent type. Now, so let us see the HS diagram. So here it says it is P1 at 200 degrees centigrade. So you need to find the point 1. And after it is isentropic expansion takes place up to throat, because we need throat is the area where we have the minimum area. So hence here we are using only the two pressure conditions, P1 inlet area and the throat P2, since we need to find the area at the throat region. So to find the area at the throat region, we use the formula mass flow rate. So M is equal to rho 2 A2 V2. What is rho 2? Rho 2 is the density of the steam at the throat, A2 is the area at the throat, and V2 is the velocity at the throat. But density, what is the unit of density? It is kg per meter cube. If you take the reciprocal of it, you get it as meter cube per kg. That is nothing but the specific volume. So here I am considering throughout this steam nozzle chapter, we use density in terms of 1 by specific volume, that is small v2. And so what will be M will be equal to A2 into capital V2, that is velocity, divided by the specific volume small V2. But we need to find the velocity. So what is A2 will be equal to M into small v2 by capital V2. So for that you need to find the values of specific volume and the velocity at the throat to find the area. So how do you find the velocity? V2 is equal to square root of h1 minus h2. Since 2 is in the region of wet steam, that means since 2 is a wet steam, we need to find the value of x2. Then if you get the value of x2, specific value V2 will be equal to x2 into Vg2. That is at the pressure 5.46 bar, get the value of Vg and substitute here, multiply by the dryness fraction, will get the specific steam value at nozzle. Okay, now let us solve this problem using steam tables. So for superheated steam for P1 10 bar, T1 200 degrees centigrade, go to the superheated steam table, get the value of H1 and S1. Also from steam tables, get the value of Vg2 for the pressure 5.46. Get the value of SF2, SFG2, SFG2, VG2, these three values for the pressure 5.46. And we know S1 is equal to S2 since it is isentropic expansion. So S1 we can directly get from the superheated table, that will be equal to S2. S2 you cannot get directly because it is in the wet region. So using this condition S1 equals S2, we will find out the value of X2, that is dryness fraction. So SF2, that means 2 means it is a pressure of 5.46. Go to steam tables, get SF2, SFG2, HF2, HFG2 and VG2, all these values for this pressure 5.46, and so substitute SF2 and SFG2, get the value of X2. So that is X2 dryness fraction at 2 is 0.982. So then substitute here to get the value of H2. H2 is equal to HF2 plus X2 into HF2, you will get 2713 kilojoules per kg. Then specific volume, multiply by dryness fraction, you get the specific value. Then area is obtained by using M into specific volume divided by velocity at the throat. That will be equal to M into specific divided by square root of velocity. How do you find velocity? It will be square root of 2 times H1 minus H2. So since you know the value of H1 and H2 and V2, we can get the area. So 3 into what is V2? is 0.339 divided by square root of 2 times H1 minus H2. So H1 is 2826 and H2 is 2713. So please don't forget to multiply by 10 power of 3. So then you will get the area as 2.13 into 10 power of minus 3 meters square. Okay, then let's go to the next problem, the third problem, where it says the adiabatic steam nozzle is to be designed. That means you need to find out the dimensions of a nozzle for a discharge. They are given the discharge as 10 kg per second. And the entry steam value is 10 bar 400 degrees centigrade is expanded isentropically to 1 bar pressure. The nozzle efficiency is given as 0.92 and they said the frictional losses is assumed to take place in the divergent portion of the nozzle only. That means the nozzle is of convergent divergent part and the frictional losses occurs only in the divergent part. So you need to find out, so since you are designing a nozzle, you need to find the velocity of the steam at the throat and the exit of the nozzle, and similarly the area at the throat and the exit. Assume expansion of index of expansion as 1.3 since the entry steam is superheated. Now, so the sketch is given here. So 1 is the nozzle entry region and 2 is the throat region and 3 is the nozzle convergent divergent nozzle exit. So given data, pressure of the steam at entry is given as 10 bar 400 degrees centigrade and exit, that means at 3 it is given as 1 bar. So first thing what you need to do, find the pressure at the throat. How do you find? Using the, you need to find using the critical pressure ratio. So P2 will be equal to P1 into 2 by n plus 1 power n by n minus 1. N value is 1.3 since it is superheated and P1 value is given as 10 bar. So get the value of P2. So what is the P2 value is 5.46 bar. So now here this problem, since it is bit lengthy, this problem is solved using Molière diagram. So what the Molière diagram is, how to use the Molière diagram is explained in the previous lecture. Now let us see here once again. So this is the HS diagram. So mark the point 1. That means where this 10 bar pressure line cuts the temperature line at 400 degrees centigrade. So mark that point as 1. Then draw a vertical line till it cuts the 1 bar pressure line because the pressure at the exit of the nozzle is 1 bar. So draw a line where it cuts the 1 bar pressure line. One thing you need to note here, this cuts in the superheated. That means the nozzle which is coming, the steam which is coming out of the nozzle is also superheated. In the previous cases, we considered as the wet steam which is coming out of the nozzle. But here it is in the superheated region only. So, and we have also find out the pressure at the throat. So mark the point along this vertical line where the pressure 5.46 pressure line cuts this vertical line. So mark this point as 2. Okay. Now, it's also said there is loss, that is frictional losses occur in the divergent part. That means from 1 to 2 is the convergent part and 2 to 3 is the divergent part. So in the divergent part, that is 2 to 3, frictional losses occur. Hence, the exit condition of the steam or the exit enthalpy of the steam is less than the actual isentropic, or the theoretical condition of the steam is less than the actual condition of the steam, due to frictional heating of the steam. Okay, so now what are the data you need to find out from the Molière diagram for solving the problems? So at point number 1, get the value of H1 and S1. So S1 you need not find out. Next, at point number 2, draw this line. So at point number 2, draw a horizontal line, get the value of H2. Then, since it is at 2, to calculate the area, you need the specific volume. So, and as I said, the specific volume lines are dotted lines which runs next to this pressure lines. So, get the value of V2. So you need to find the value of H2 and specific volume V2 at the point 2. Similarly, go to the point 3, get the value of H3 and the specific volume at 3, but actually you need to have it at 3 dash. Get the specific volume at 3 dash. Now, first we'll find out the area at the throat. So use the formula m dot is equal to A2 into velocity V2 divided by small v2. Please make a note of the difference between the V values here. This V is the velocity and this V is the specific volume. So what is A2 is equal to mass flow rate into specific volume divided by velocity of the steam. That will be, so 10 into what is the specific volume, if you can say it becomes 0.5 divided by velocity which we found out here. So 2 times h1 minus h2, get the velocity of the steam at throat. So then substitute here, you'll get the area. These two conditions we have found out velocity and area at the throat. Now we'll go to find out the velocity at the exit. So that will be equal to square root of 2 times the actual enthalpy drop, H2 minus H3 dash. So, but from the nozzle efficiency equation, we know it is nothing but the ratio of actual enthalpy drop by isentropic drop. So, actual enthalpy drop will be equal to nozzle efficiency into isentropic enthalpy drop. So, nozzle efficiency is 0.92. So, because that is the efficiency given, and multiply by H1 minus H, we are taken directly H1 minus H3. Okay, so H1 minus H3 into 10 power of 3. Please don't forget. So then you will get the value of velocity at the exit of the nozzle. Then substitute here in the mass flow rate equation again to get the area. And V3 will be is from the specific volume at the point 3 dash. It should be actually V3 dash. Okay, divided by V3. V3 is a thing, but again V3 dash. So get the value of area at the exit. Further problems will continue in my next lecture. Thank you.